little bit more realistic. It's a little bit more complex. And so it's for a well. And again, it's, the vertical axis is depth. And the horizontal is some of the different elements. Well, here's a gamma ray log. This one's got TOC. These orange dots are TOC. Titanium, zirconium, a silica to aluminum ratio, aluminum, potassium, calcium, so on. So let's do an interpretation of this now. So first of all, what is the mineral composition? And we'll look at calcium, for example. Here you see, that's this column right here is calcium. Right there. And you see a high peak of calcium there. Another one there. Whoops. Another one there, there. A zone of a lot of calcium there. And there. There. Okay, so imagine now the stratigraphy. You're going to have these zones here are all calcite rich. They have very low silica to aluminum. They have very low clay content and so on. So we've got part of the stratigraphy. We've got these calcium hard streaks or intervals. Now let's look at the silica-aluminum ratio. Here's a high peak for silica-aluminum, high peak for silica-aluminum, high peak there, some high peaks over here. Those high areas are where you have high silica to aluminum, where you're likely to have that biogenic quartz. Biogenic silica, if you want to call it that. And if you look now, you have to really look closely. These two little peaks of high silica to aluminum ratio correspond to these two peaks of low aluminum and these two peaks of low potassium. So in other words, what it's saying is that you've got these intervals that if you've got a high silica to aluminum ratio and little to no aluminum, potassium, same thing with titanium, not much titanium, and so on, that must mean that those are biogenic quartz. So now we've been able to identify a potential fracturable intervals where we had those high silica to aluminum ratios, and we were able to verify that by the low amount of aluminum, low potassium, and so on. So now we've got some calcite streaks that are brittle and some quartz streaks that are brittle in here. And the rest of this is basically going to be clay-rich shale. So like an interval in here, well, let's see, let's take, okay, an interval here where you have a fairly high potassium. That's an indicator of clay minerals. So where you've got clay minerals, you're also going to have organic matter, so you get fairly high organic matter down here, that interval, and so on. So now by doing this very rapid analysis, you can work out the entire stratigraphy and determine which zones are going to be brittle, and the ductile zones are going to be the ones that contain a lot of clay and not much silica or calcium. So we can now make a log, a geomechanical log, brittle, ductile, that's what we do. And that allows us to narrow in on what intervals might be the most prospective for a horizontal well. So interval of very high silica to aluminum, meaning that this is really a very silica-rich or quartz-rich interval. And an interval here where you have a very low silica to aluminum. So this is going to be a very ductile interval, okay, with lots of clay minerals, not much quartz. So you work out your, yeah.
At which depth are you?
Well, this is at about 225 feet.
Oh, okay. Thank you.
This one's about 370. It's backwards here because this actually was an outcrop that we did this. Not a well, but an outcrop. And the student was an ex-engineer. See, and went from the top down. No, geologist, I'm sorry. Went from the bottom up, okay, from 0 to 400 feet. So that was a geologist that did that. Okay, so you can work out your stratigraphy, you can work out where's brittle rock, where's ductile rock, you can work out where your organic rich rocks are, which are going to be your hydrocarbon source rocks, and where your hydrocarbon poor rocks will be, or where you have a low TOC. All right, well, let's look at a stratigraphic aspect now. Just like we've been talking about, I'm going to go back to sequence stratigraphy for a couple of minutes and show you, this is a 3D seismic horizon from the Woodford Shale area. And what you see here is an isopac map of the thickness of the Woodford Shale. What you see is one area that's quite thick down here, and another area that's quite thick. The thick areas are the reds, the yellows, and the greens. And then you've got the blue areas, which are thin. So the Woodford is a variable thickness here. Okay? It's not a uniform shale of uniform thickness by any means. So let's draw cross sections through there. And let's take this red one first. Let's take this red cross section. And we're going to go back now. Remember that Hunton unconformity. Here's the upper surface of that Hunton unconformity. And I'm tracing it now in blue, in yellow. And let's take this blue cross section. And I'm going to do the same thing. What have I drawn? Okay, what have I drawn there? You've got two thick areas, and I've drawn cross sections across those two thick areas. I've drawn incised valleys, or some sort of a depression. Because it's long like this, it's most likely an incised valley. And so that was, remember I said at the beginning, the formation down here is called the Hunton limestone. So it was deposited, it's shown in blue here. It was deposited. Then you had a sea level drop, which caused the unconformity surface. And then you had a rise in sea level that you had backfilling all these different colors of the Woodford Shale. Now, why you get all these different colors is we were able to for example, take our chemostratigraphy and correlate that we had different shales or different stratigraphic intervals. So we took this, did the type of analysis I just pointed out. We've got some calcite bands there and some organic rich bands here and clay intervals here, and we put those into the cross section. And so that's what all these different colors are. So these different colors represent different strata with different properties. So it's not a uniform black shale. It's quite complex stratigraphically, the shale. And one of the mistakes that we see a lot, and that we've mentioned to a number of companies, is that you may drill a well here, and you say, well, here's the Woodford, and then you drill a well here, and you say, well, here's the Woodford, it's thicker here, but it's probably the same rock type. Okay? But when you do this sort of, that's if you don't do any more analyses, but when you do this sort of analysis, you actually see different layers here in this well than you do there. So particularly the lower ones, this turquoise blue one that I just pointed to, pinches out along the sides of that valley. So it's not present in this well, and yet it may be the most favorable horizontal target zone. And if you're a novice at this, you drill the well and say, well, you know, here's the Woodford, there's the Woodford, it's all the same. Not going to be true. And so you can miss your good zones by not doing this sort of work. Let's look at, here's the same two Incise Valley fills. And now we'll look down the axis longitudinally at this red line, and that's this cross section there. And again, the unconformity comes along just like that. And there's the top of the Woodford. Didn't draw it well again, but top of the Woodford. Here's a green cross-section line. That's this one down here. And the same thing. You see variations in the topography of the underlying Hutton formation. And you get different layers, different types of layers in different wells. So not always are you going to get the same layer in different wells. Well, here's a cross-section that goes across both of these Incise valleys, goes across like this, and here it is here. And so E is over here, the east end, or E end of the cross-section, and you see the very irregular surface on the top of the Hutton. That unconformity is very irregular here, and also when you cross that Incise Valley. Very irregular surface. Well, it turns out then, if you want to look for the thickest, well, one of the things you would want to do probably is look for the thickest Woodford, more potential reservoir and source rock. And you might find where it's thicker, you've got more potential productivity. So we would like to do that. So it becomes important to understand why you have a thicker Woodford here, for example, in this well, and a very thin one in that well. So what I've done here is I've just kind of reconstructed a cartoon style of what you're seeing here. This is the Hunton unconformity, and here's the topographic irregularity on that unconformity. I'm going to skip some of these because we're running low on time. So going from this picture, this is the irregular surface on the unconformity. Here it is right here. So let's go through a sea level cycle now. We're going to bring this back to sequence stratigraphy. You started out with a falling stage of sea level. Well, you started out with a high stand of sea level when the Hunton limestone was deposited. Okay? Then you had a drop in sea level, so you created that unconformity. Then you had a rise in sea level where you backfilled those topographic depressions. Okay, so if we look at that in this little diagram, I'm starting out with a high stand of sea level. Okay, so here's my sea surface up here, and I've got some topographic irregularity here. So let's say I have a topographic depression right here and a deeper one down there. Well, I start, We go from our high stand, now we're going to start to drop sea level. So we have a fall. What happens with the fall in sea level? Well, in some of these topographic depressions, you trap the water and the sediment. In other words, the blue up here was, we'll say, marine water, the ocean. But when you lower sea level, now you've kind of trapped that in this area here. You've trapped that and you've created kind of a semi-enclosed basin. Well, we all know that semi-enclosed basins tend to not have very good circulation, and you may have organic matter deposited, but if you've got poor circulation, and I'm going to jump ahead a little bit here, if you've got a setting, a marine setting, where you don't have much oxygen in the water, when you deposit organic material, it will be preserved. If you have a very oxygen-rich water column and you deposit organic matter, the organic matter becomes oxidized and destroyed. So the organic-rich intervals that you're going to have must have been deposited. If you've got organic materials in your rocks, they must have been deposited in an environment where you did not have good circulation, so you did not have very much oxygen content. And so the organic matter, as it fell to the bottom, it got preserved. So this little black stuff up in here that you see is preserved organic matter, and it's isolated because of the underlying topography. Now let's start to raise sea level. So we'll start to raise sea level, and we continue to raise sea level. We might at this point still be depositing in a semi-enclosed basin, but by the time we get up to this position, where our sea surface is up here now, we start to get circulation of the ocean water, so no longer is any organic matter going to be preserved. and then with the continued high stand in sea level, you'll get sediment deposited that will not have organic matter in it. So, what this tells you is you've got a stratification of your source rock or your organic matter. Well, it was at one time a hypothetical model because one of the things that you see in a lot of these shales is if you look at a gamma ray log, you get something like this, and then boom, you get a very sharp increase in gamma ray content, and then it goes like this, meaning that you have your high organic matter down here, sitting on an unconformity surface, and maybe your Hunton limestone down here with a very low gamma ray. And as you're moving up in the stratigraphic section, you're getting cleaner and cleaner sediments, less and less organic matter, because you reach this zone where you get oceanic circulation between the open ocean water here and the water that was in that restricted semi-enclosed basin. And so this is typically the pattern that you see. Well, if we take this, where would you want to drill your well? If this were a well log, and you had narrowed down to 2 positions there, where would you want to drill? Well, where I'd want to drill would be, I'd want to drill in this interval here. It's cleaner, it's got less organic matter, and because it's cleaner, it's probably got some good brittle minerals making up the rock, like quartz and calcite. Whereas down here, I'm going to have all my clays with my sticky clays with the organic matter. And if I were to drill my well down here, the pipe would stick, or the bit would stick, and you'd lose the hole, or whatever happens at that point. So you want to be very careful then when you see patterns like this as to where you put your horizontal well bore. Okay.
So there's a question. So we want to drill where it's more brittle, right? We got a better chance of not getting the tool stuck. But then that area doesn't have enough organic matter. So that's why we fracture to connect to that area.
Right. So you drill your well here, you fracture it there, fractures go down, and the hydrocarbons come up into the fracture zone. If you drill into the ductile zone, the organic rich, you're going to get a stuck pipe or a bit, because it's sticky and gooey and ductile. Yeah. So that's the drilling concept that we've come up with. Now, can we prove this model? Well, we set out to prove it, and sure enough, we could. And so what you're looking at is a 3D seismic survey, and you're looking at a vertical line here, vertical seismic line, and the scale, the color scale here is in TOC, total organic carbon. Notice that the total organic carbon, so the highest organic carbon in this interval is in yellow, around about 8% TOC. Well, notice that it's not uniformly distributed, but it's a very patchy distribution in the plan view, in the cross section. You've got a good high TOC zone here, and another good one right down there where you've got the yellows, and then you go up a little higher and you've got another good one, and another good one. And you can, in this case, we could calibrate with a well log, so we knew how much our TOC was, and it fit what we saw from the seismic. Now, so that's what we saw from the seismic when we looked at a cross-sectional view. How about when we look at a horizontal view, the horizon slice? Well, we took 4 horizon slices in this stratigraphic interval. We did one down here, one a little bit higher, one higher, and so on. And I'm just going to show you the bottommost one now, the one that we took down through here, kind of like that. And this is the horizon slice for that interval. And what do you see? You see a very patchy distribution of yellow, meaning it's a patchy distribution of organic matter. So that was the first line of evidence that maybe this model that we had built was valid. In other words, what we were looking at were these little depressions where you'd get localized accumulation of organic matter. And so when one well would be drilled, maybe in this yellow zone where you had high TOC, and it's a good well, and then you go over here in the blue and you drill a well not too far away, and it's no good. It's because of this level of compartmentalization, all due to the way in which the rocks were deposited. The way in which the rocks were deposited. So I won't go up and show you the others, but they're stratigraphically higher, but that makes the point. I think you can see that you've got this patchy distribution. You also get some linear patterns, like I showed before, of high TOC. So you now have picked out your drilling targets, or your potential drilling targets, where you're going to have TOC. Now you don't drill into those patchy high TOC because they're going to be ductile, but you drill above them and you get your ductile, your brittle rock, you fracture into it, and the hydrocarbons come out of the yellow and into the brittle rock, and you've got a good well. So, more TOC near the base of the Woodford and a very patchy distribution of the TOC, all kind of supporting this depositional model that we have for the patchy distribution of the organic matter. Well, there's another example that showed the same thing, and I'll show it to you quickly. This is a 3D seismic survey looking at a horizon near the bottom of the Woodford, right above that unconformity. There's a fault through here. There's the fault. And once again, the high TOC is in yellow. Actually, the TOC is up to 13% here. So it's a really nice source rock. Notice that the TOC is not distributed uniformly across that whole stratigraphic section, but it's near the bottom. According to our model, that's where you would have your preservation of your organic matter during deposition. You would have had a depression there that preserved the that gave you kind of restricted oceanic circulation, not much oxygen, so you get preservation of the organic matter. So that was another a good test case for our model. When we looked at the well log, one of the well logs looked something like this. Here was your Hunton limestone down here, and you had a very high gamma ray kick right at the bottom, and then a reduction, and a high frequency cycle that gave you another high gamma ray kick, condensed section, and so on. So here you see the effects of these high frequency cycles on your shale stratigraphy. So where are you going to drill your well here? Well, I drill my well right in here. I wouldn't want to drill it here because it's going to be sticky. It's going to be full of clay and organic matter. But if I drill it here and then frack it through there, I frack that rock, and hydrocarbons that are in that rock get up into the brittle zone, the reservoir zone. Skip that. So the same principles apply. Let's draw a sea level curve here. So you sea level rise, you deposited the Hunton Formation. Sea level starts to drop. You create the erosional unconformity. You build up your topography and sites, valleys, and things. You build that up there during the fall. You fill the incised valleys during the rise. During early rise, you're going to have deposition in some areas in these semi-enclosed basins, but not everywhere, because you have this irregular topography. So in areas where you do have those depressions, you are going to preserve organic matter on this part of our sea level curve, the lower part. Transgressive, remember transgressive marine. And then in the upper part, with your sea level rising, so you get open ocean communication between those isolated basins and the open ocean, so you have better circulation, more oxygen in the water, so you oxidize any organic matter, and so you lose it, you dissolve it. And so that would occur up in this interval here. And then there is a higher order of frequency that I'm not going to bother with now because of the time. So, same principles that I used for the sequence stratigraphy of the sandstones that you can use for the shales. Now, to just go through a couple of quick things, I think I'll skip the geochemistry, the thermal maturity and stuff, and get on with the geomechanical properties. All right, let's look at the geomechanical properties a little bit now, at least the way we do it. We're a pretty low-cost operation, so you're going to see some very inexpensive equipment here, not like these big triaxial chambers and things. Our petroleum engineers have those in their department. My department, we have a cheaper thing that works, we think, pretty well. So brittleness evaluation methods, and again, I'll use the Woodford as an example. So what is brittleness? You know, it's you can apply a stress, and the rock, you'll strain the rock, and in a brittle rock, you'll get a break, a sharp break, at which you get fracturing. Whereas in a ductile rock, the state of stress stretches out, even when you apply a lot of strain, until you get breakage there. So that would be a ductile rock, and the first one would be a brittle rock. That would be a ductile rock and a brittle rock. wake up to do that? This guy's mad and wants to go home. So he's demonstrating, this guy's demonstrating brittle rock, okay? And using glass as the example. The ductile rock is something like this. You can squeeze and squeeze and squeeze, and you rarely ever fracture it. Okay, so that's the geologist's difference between brittle and ductile rocks. Okay. So you get a clay-rich rock. This one actually did break a little bit, but certainly not as good a breakage as your quartz-rich brittle rock. Okay, that broke into a lot of pieces. Well, different people again have different terminologies, and here's what drillers often do. And geologists, they say, well, I got a ductile rock or I got a brittle rock. Okay. Well, what that means is that it takes a lot of pumping to break or pressurizing to break that ductile rock up, and it doesn't take as much pressurizing to break the ductile rock up. So that's your brittle rock. Fracture gradient is high here and lower in your brittle rock. Well, one way in which us geologists measure brittleness is what we call a brittleness index. And what a brittleness index is, it's a measure of the mineral composition of the rock. And so what you see is a common equation down here, where BI stands for brittleness index. Q stands for quartz. Quartz is a mineral that is brittle. Dolomite is a rock that it's a calcium magnesium rich rock that is brittle. And carbonate, limestone, is also a rock that's brittle. So you just you do an analysis. Let's say you send off your 1,000 samples for X-ray diffraction, and you get this table back with all your different minerals. Or you can do it the easy way with the X-ray fluorescence, the XRF chemical analysis, and convert the chemistry to the mineralogy. And then just build this equation here, where your quartz plus dolomite plus limestone, those are your three, I should say calcite, not limestone. Those are your three minerals that give brittleness to the rock. The ones that give ductility to the rock are the clay minerals, Cl for clay mineral, and TOC. Okay, provides ductility to the rock. So if you just divide the brittle minerals, the minerals that give brittleness, by the whole mineral composition of the rock, you'll get a number, a fractional number called the brittleness index. And I don't have a scale to show you, but the brittleness index would be anywhere from 0 to 1, okay? Because it's fractional here. So 0 to 1. Now,
excuse me,
yeah.
I get these numbers from the XRF, right?
You can either get, you get them from the XRF, you get the chemistry, you convert the chemistry to the minerals, and you put the mineral abundance in the equation. Or you can do X-ray diffraction, which I said is another technique for minerals, more expensive, more time consuming, so you don't usually do a large number of samples. But you can do it that way too. Okay, so now we've got a number here, Now let's put this in terms of something you're more familiar with, say like Young's modulus and Poisson's ratio. And I'll do a cross plot here of Young's modulus versus Poisson's ratio. And I have Poisson's ratio increasing from left to right. But I have Young's modulus now increasing from bottom to top, not like most graphs that go from bottom. They increase from bottom to top. This plot, the way it's made, is you have your highest Young's modulus number down at the bottom, and the lowest number 0 at the top. Well, if you have a Poisson's ratio, let's say of 0.30, you measure Poisson's ratio, which is a measure of the deformation of the rock, and it's 0.30, you fall in there, and the Young's modulus is 4.0 you measure. You've got a rock that falls in here. Well, we can also superimpose the brittleness index at this position. This has been all calculated. This is a valid global type plot that you can use, and which shows brittleness index. And high is red and low is gray. So high Young's modulus and low Poisson's ratio defines a brittle rock. And high Poisson's ratio and low Young's modulus defines a ductile rock. So these are measurements that you can make in the lab, geomechanical measurements that you can apply to your reservoir. Now again, it takes a lot of time and effort to measure Young's modulus and Poisson's ratio, and so you can do a faster job, really, the old geologist way with the X-ray fluorescence. Okay, and just use this scale here as it's shown. That's a global correct scale. But at any rate, so your combination of Poisson's ratio and Young's modulus, which I'm assuming you're all familiar with, is a measure of the brittleness or ductility of the rock. Now, to show you the effect, this is always strikes me as very amazing. When I look at the effect of slight changes in brittleness and ductility of a rock, what a pronounced effect that has on the fracture potential of the rock. So here we have a ductile rock, and here we have a brittle rock, and then a ductile rock below. Now look at this. Now this rock, look at the scale here. This is 20 millimeters. Okay, a really thin bed of brittle rock sandwiched between two beds of ductile rock. And what do you see? You see a fracture that goes through the brittle rock and stops at the ductile rock boundary. And that's pretty impressive to me that the different changes in brittleness and ductility have that such a pronounced effect. And so here's an example. This is an outcrop example where we've got alternating brittle silica-rich rock and ductile clay organic-rich rock. So here's the brittle rock. Another one there, and so on, and there. And the ductile rock the oh, okay. What you see here is a picture now, a kind of like a sketch of what you see in this outcrop. So what do you see? If you look, you got to really look closely here, that the ductile rock, the ductile layers, don't have any fractures through them, or very few fractures. Whereas the brittle layers have a lot of fractures going through them. And that's what you see in nature, not just confined to these types of rocks, but anything. If you've got a limestone with a shale below, you'll usually see the fracture going through the limestone, and that fracture stops at the shale. It doesn't go through at all, because you've gone from a brittle rock to a ductile rock. And it's the same thing, but what amazes me is that occurs at this very fine scale. Very fine scale that occurs. And that's what's going to be your reservoir ultimately. It's not going to be fractured throughout like that. It's going to have a brittle fractured zone, a ductile non-fractured zone, brittle fractured zone, and so on. Now this is a small scale example, but we see the same thing at larger scale. So if you were going to measure brittleness, sample-based brittleness from core or outcrop, you would use the X-ray diffraction to get your mineral composition, or you could do it from the X-ray fluorescence. And what I want to talk about now, show you, is this rebound hammer, which is the instrument that we use. Well, before I do that, this is an equation that we have developed. Yes, geologists do equations sometimes. And this is one that we developed from the X-ray fluorescence. So if you can see the fine print down here, we've got the amount of illite in the rock equals 0.001095 times the potassium content. K is potassium. Plus 0.004810 times the aluminum content. Okay, when we add those two together, we can make an estimate then of how much illite, clay mineral, there is in the rock. Similarly, for quartz, we do the silica to titanium ratio minus 0.01086 plus 0.0002759 silica, and that'll tell us how much quartz we've got. So it's a way of quantifying, of going from that XRF, which is easier and cheaper, to the mineralogy, and then plot the mineralogy in our equation, and we get a brittleness index that way. So we have our, we can calculate the amount of illite by the amount of potassium and aluminum. We can calculate the amount of quartz by the silica-titanium ratio and how much silica there is. Amount of dolomite, so on, and calcite and kaolinite clay.
Dr. Slatt,
Yeah.
On the question, does the elite and the kaolinite adds up to the Cl double clay term in your equation?
I'm sorry, I didn't.
You have a clay term.
Yeah.
Uh,
Yeah, I combined the illite and the kaolinite.
so they are.
Yeah. So they're combined here in this clay parameter.
Okay.
Yeah. So we've tested our equation. We've tested it, for example, by taking X-ray diffraction measurements of the mineralogy and then doing our X-ray fluorescence measurements of the chemistry, and we get pretty good agreement here. This is about a 77% R squared, so that's pretty good for us geologists. Now, we would like to be a little more, this is an indirect measure of the geomechanics. We would like to be a little more direct in our methodology. So the engineers over at OU, for example, they have the triaxial chambers and all of those instruments. And us geologists, I think we paid $1,500 for this little thing here called a micro rebound hammer. And this is it. It's about 15 centimeters high. And what you do is it's spring loaded with a little diamond chip down at the bottom. And you just lift it up, that handle, and drop it. And you measure the intensity that little diamond chip hits the rock. You measure the amount of indentation of the rock. That's going to be a measure of the brittleness. So this is the instrument we use, and it's a super duper instrument because it's so small that we can actually get down and make measurements of the rock property, the geomechanical properties, at the same scale as we do the XRF, a very fine scale. In fact, if you had the time, you could do an infinite geomechanical log, and this you do get a numerical value when when that hits. So you can convert this how hard this diamond chip hits the rock, and you can convert that to Poisson's ratio and Young's modulus once you calibrate with some sample rocks. And just some of the work we've done. Here's your hardness from the rebound hammer versus brittleness index calculated from the measurement of the mineral content, and you see you get a pretty good straight line, a linear relationship. And in this case, the more silica you've got in the rock, the harder the rock is, and the more brittle it is. Except you have this anomaly down here, which is really another type of rock. A dolomitic mudstone doesn't have any silica in it. It's all mineral dolomite, which is also a hard mineral, but not as hard as the quartz. So it plots down here. The brittleness index versus your hardness. Yeah.
Can we assume that the argillaceous shell will be rich organic shell?
The which ones?
The argillaceous. The one that has the lowest brittleness.
Yeah, it would in this particular example, the argillaceous shale would be the one that would be argillaceous, meaning clay. So it would be the one that would be most apt to have the high TOCs. Yeah. So here's some other experiments we've done where we measure brittleness index versus rock type. And so your high clay has the lowest brittleness index, and quartz and dolomite have the highest brittleness index. But interestingly enough, when you go to rock type versus hardness, as measured with that little little hardness rebound tester, your dolomite drops down somewhat. So it's not way up here. So in terms of your mineralogy, it plots pretty high up in brittleness index, but in true hardness, measured by the rebound hammer, it's not as brittle. So you can, you've got core. We've done this with cuttings too, by the way. You can, in fact, we helped position a horizontal well. We had cuttings at 10-meter intervals, and they wanted to know the best landing zone for a horizontal well. They didn't have any core or anything, but they did have cuttings. So we took the cuttings, we crushed them up, and did the XRF on the mixture, the powder, and we're able to, even though it's wide, what represents a 10-meter range of rock, we were able to see differences in the chemistry that allowed us to find and keep the horizontal wellbore into the target zone. So you can do this with cuttings as well. I think I may have that. I can show that to you. Let's see. Oh yeah, I'll do that first. Yeah, sure. Well, maybe I won't. I'm not going to show that, but we were able to pick the target zone from the XRF analyses of the cuttings in a horizontal well. Now, if you want a good research area to study, if you want to really, in my geologic opinion, add to what we know and don't know about brittleness, we look at anisotropy, or in geology terms, the layering of the rock. And if there were a way, layering in the rock is important in affecting the breakability of the rock. I'll use the word breakability rather than fracturability, but breakability of the rock. So here's some core, for example. And these are different layers, very thin layers. Well, each one of these layers represents a single deposit. Okay, so you had some mud come down, deposited in one layer, and then sometime later you had another layer come down and deposited. So each layer is a single geological sedimentation event. So what that means is that the boundary between those layers is weak. It's going to be weak. It's not going to be chemically bonded at all. It's just going to be a physical boundary between two depositional units, even though they're very small. Just to show you what I mean by that, here's an example under a scanning electron microscope of one of these little planes between two rock types. Here we've got a one of these radiolarian. We'll go back to the radiolarian, the Woodford. This is a radiolarian-rich rock. It's going to be brittle. Here's a dolomite-rich rock that's also going to be brittle, but still it breaks. And it breaks at this plane between the two, because this is just a physical boundary where you had deposition of the dolomite-rich rock and then deposition of the radiolarian-rich rock. So that boundary becomes a physical plane of weakness. And I know that engineers have a parameter, anisotropy, and it's used, but I think the anisotropy that the engineers work with, I think, is a little bit coarser scale. I'm talking about really fine scale stuff here. And I don't know if the measurements calculate the anisotropy that way. So a good area of research would be to figure out, how can I come up with a number? How can I quantify the degree of layering? Because that's going to affect the breakability of the rock. How can I do that and add it? How can I do that and add that term to my brittleness index equation, which is based on the mineralogy? And if I could do that, I think I would have a breakthrough in better understanding how the rocks break, and in particular, how the rocks break when your well is oriented at different angles relative to the plane of the bed. I don't know if I've got a picture of that or not to show you. Let's see. I guess I don't. But at any rate, here's a little experiment we did several years ago. Neville, you know this guy. This is forget his name now. Oh, Rafael Sierra. Okay, this is a student that you used to go to school with. And this is an experiment, one of the experiments he did for his master's degree at OU, where we took a rock that was very highly layered, like this, very small layers. This is about a core plug size. And what we did is we put it into a triaxial machine at different angles. So we put in one set of experiments, we had our layers parallel to the orientation of the load. And in the other case, we had our load perpendicular to the orientation of the layers. And the results, we did that for 4 different rocks with this degree of layering, but they had slightly different mineral compositions. In this case, we used a carbonate mineral, a rock with some carbonate minerals in it. So what we did, or what Raphael did, is he would apply the load in this orientation, and when he did that, he got the tensile strength way down here. Way down here. When he applied the load in this orientation, same sample, or a split of the same sample, plotted up there. That particular sample had 3% calcite in it, calcium carbonate. So we took another one that had similar layering, but it had a little more carbonate with it. And same thing, when the load was applied this way, you got a low tensile strength. And when the load was applied this way, you got a high tensile strength. Did that for a third sample with some more calcite in it. Same phenomena here and there. And he did a fourth measurement here too, with about 38% carbonate, and tensile strength plotted here for load parallel to layering, and up here load perpendicular to layering. So what that tells you, and that's not surprising, you know, I mean, I could take this set here and I get nothing happens to it. But if I do it this way and hit it, it's going to crack and crumble and all that. So I mean, it's a no-brainer, but still, it's going to be important, and it's going to be a factor in the breakability of your rock. So if you have a well bore, for example, let's say you have rocks that are horizontally bedded in the well. So if you drill your well this way, vertical well, you're going to get a certain tensile strength. But if your well is drilled this way at right angles, you're going to get a lower tensile strength. And if your well is oriented at a slant relative to the horizontal bedding, you're going to get still another tensile strength. So this is a factor that I don't, at least from a geologic perspective, I don't think has been worked out yet. But what would be really neat for research is to, we're kind of working on some of this, would be to try and come up with a factor that we could apply to the brittleness factor, brittleness index, so that we would not only be measuring the effect of mineralogy on brittleness, but we'd also be the effect of the layering, with the anisotropy. So that would be pretty good, I think. Well, I don't know. I'm about worn out, I think. We're all probably worn out for the week. I do want to hand out the diplomas. Let's see if there's anything else to talk about here. Well, let me just show you one more example of how we use seismic to, let's see, I'm going to show you two quick examples. One, I just want to finish up with, I've just shown you an example where you use the rocks to evaluate brittleness from a geologic perspective. And I just want to show you a couple more slides using logs and then using seismic to evaluate brittleness. Then we'll be finished, I think. Okay, so I've been through the rocks. Just want to give you one quick log example. Here's another example of some work we did. This is actually another outcrop of the Woodford. And we drilled a well behind this outcrop. And we cored the well behind the outcrop, and we took logs. So here's a gamma ray log of what the Woodford looked like in that particular well. Here's a sonic log, a density log, and a neutron porosity log. And we took the sonic and the density and multiplied them so we could get an acoustic impedance log. acoustic impedance is the product of density times velocity. So here was an acoustic impedance log that we developed from the sonic and the density log. And we could calculate the Young's modulus and Poisson's ratio with the logs. And so we did that. And we get one curve for, this is the Young's modulus equation. Here's the Poisson's ratio equation. And so we have two curves here that you see. What we found when we did this was that when your two curves cross, just like if you were looking for gas sand, in this case, where your two logs cross, like here, here, there, and there, those are going to be ductile zones. Okay, those are brittle zones, where you get the high Poisson's ratio and low Young's modulus. When they cross over, you're going to get a brittle rock. And just the opposite, when you don't get crossover, you've got a ductile rock. So from the logs, we could determine the degree of, using Poisson's ratio, and Poisson's ratio, Young's modulus, and acoustic impedance, we could determine which were the brittle zones and which were the ductile zones. And as you might expect, if you're at all familiar with what acoustic impedance is, again, it's the product of velocity times density, and wherever you had that crossover, you had a high acoustic impedance. And that's exactly what you would expect to find. High acoustic impedance corresponding to brittle rock that has a high Poisson's ratio and a low Young's modulus. So that's just one example of using a log-based example. I just want to finish with one showing the seismic. Now seismic based, and I've shown you a couple of examples of that already, but I'm going to show you one more. Here's the Woodford shale. This interval here in yellow and green is the Woodford, and that Hunton limestone is below it. Okay, and the unconformity would be right at the contact between the top of the blue Hunton and the bottom of the Woodford, which is the bottom of the red. And what you see is that there's variations, and this is a seismic line that was calibrated to a well log, and so we're able to convert this from a seismic amplitude line to an acoustic impedance line. So this is a measure of acoustic impedance, and the cool colors are high impedance, and the hot colors are low impedance. So what we have here in the Woodford is a lot of this is yellow. Okay, a lot of the Woodford is yellow, which is about 40 or 45 units of acoustic impedance. The green interval that you see occasionally is very discontinuous. That's a little bit lower acoustic impedance, 30 to 35. So you've got high acoustic impedance in yellow, low acoustic impedance in green. What does that mean? It means that your high organic matter rock is going to have a lower acoustic impedance than your low organic matter rock. It's going to have a higher acoustic impedance. So now, essentially, from the seismic, what you've been able to do is pick out the zones where you're going to have your highest TOC. So if I were going to drill a well here, I would drill a well that comes down, goes right in through there. Let me draw this other way. All right, if I were going to drill a well, I'd go down something like this, and I'd come in right there, right above that green zone that's going to have all the organics. The yellow zone, having a higher acoustic impedance, is not going to have as much organics. So I'd drill and frack right there, and I'd fracture down into the organic-rich green zone, and I'd have a good well. So, like I said at the beginning of all of this, our goal in shale geology, there's lots of different people have lots of different goals. My group's goal is really oriented towards finding the best landing zone. What I've tried to show you very briefly is how you do that. Now, I teach a 5-day course on this, so I've lumped that into about, an hour and a half or 2 hours. So there's lots more shale stuff, but that's probably a good place to end for the week. I don't know if you're tired, but I sure am. I've got to get on a plane at 2 a.m. this morning. And yeah.
In order to see this kind of resolution for the shale reservoirs, we can use a 3D seismic, or sometimes it's better get one 2D seismic of high resolution in the zone.
So 3D seismic of lower resolution versus 2D seismic of higher resolution. That's a hard question to answer, because the better resolution will let you pinpoint the horizon, but only in one plane or in 2 planes. And whereas the 3D allows you to map. So I think I'd go with the 3D. I'd rather have somewhat lower resolution and be able to map laterally the different units. I could map this green unit, for example, or the yellow unit. So that would be my preference. But if you've only got 2D seismic, use the 2D seismic.
And what do you think about the algorithms that are incorporated in Petrel and IP metaphysics in order to estimate the DOC?
Well, this is what we use Petrel for all of this that I've shown you. I'm not familiar with the other one you just mentioned, but we do everything with Petrel. And the reason we do that is because Schlumberger bought us a complete computing lab with 20 computers, all loaded with Petrel. So thank you, Schlumberger. And so and that was a condition that our students use Petrel, with the thought being when they graduate, they go out and beat the bushes for Petrel. Yeah. So so everything I've shown you here is with Petrel. Yeah. Okay? Yeah.
The notes that you show us in the last slide, the Poisson ratio and the Young's modulus were estimated from the conventional logs, or you get it from the well with special tools?
You get it with the well with a shear wave sonic.
Okay.
Yeah. But you can get the acoustic impedance from the conventional logs.
Yes.
And where you have high acoustic impedance, you're going to have brittle rock, and low acoustic impedance, you'll have ductile rock.
Yeah. Yes, but when we use only the compressional wave, it's not really good like the shear wave.
Yes, that's true. Yeah, it's not as good, but if you don't have anything else,
yes.
You go with what you got. Yeah. Okay. Well, the last part of the course is to hand out diplomas. Everybody passed the course, and I have diplomas for you. I don't know how you want to do this. Just how about I stand up and I'll try to properly pronounce your names, and maybe successful or maybe not. And I will say you guys have been a great class. It's been fantastic. I've really enjoyed the class because of your involvement and talking, asking questions and things like that. Sometimes I get a class where everybody sits there all week and never says anything, and I start to fall asleep and start talking about the football game or something like that. You know, so I really appreciate it. It's been great for me, and I hope you invite me back again sometime. I'd be more than happy to get on the plane and do it again. So let's see. Maisel? Blanco? Lamachi. Close enough, huh? And Alisa? Oh boy. Ilka Alejandra? I recognize Alejandra. Julio? I know Julio. Taking care of me all week, make sure I didn't get lost or anything. Pedro Marcelo? Not here, okay, I'll leave that with you. And Armin Ludwig? Sorry about that. Franco Fabian? Ariel Alejandro? Okay. Carlos Victor? And Ricardo Marcello. Okay. Everybody got a diploma. You didn't get a diploma, did you?
No, I don't do
You don't need a diploma. Okay. Okay. Okay, well that's the course then. Thank you very much once again. I hope it's been worthwhile, and I look forward to reading the newspapers about all these big new discoveries in Bolivia, and I'll know where they came from. Okay, so thank you.